I accidentally deleted the recordings of today's lecture, so that's why I'm now recording a very short summary lecture. And it may also be useful for the on-site students. After all, we started with a small quantitative exercise and we didn't get very far with the learning path of the second week of the EPA 1322 course. So let me go and let me explain very briefly on the whiteboard first what I would like to tell you about 12 functions that are used very often in simulation models, and they are really the basic functions that you need to make complex simulation models. Now, there are hundreds of other functions pre-made and available in simulation packages, but you don't need them. Most of what you will need are the functions that I will deal with now. And to really understand them well, I would like to explain you a little more than what you would discover if you would just do the exercises. So this is a small feed forward into what you're going to do in the second week. So let me start with the first function. The first function is a step function. So here we go. Step. And the step function allows you to step up at a particular moment in time. So say, for instance, that I want a step up at, for instance, moment 5, the simulation model, this is time, and I wanted to step up to the value 1, then I would write this in a particular auxiliary variable, for instance, as step with the value 1 at moment 5. This also means that you can use a step function to turn, for instance, policies on and off, but it's pretty discrete in terms of switching it on and off, but it's nevertheless very useful. So say, for instance, you want to turn a policy on at moment 5 and you want to turn it off at moment 10, then we can actually add minus step 1 at moment 10 to the variable we would, for instance, use to turn something on or off. There are other ways to do this, but this is a convenient way. Step functions are used a lot. The second function, which is a little more continuous now, at least not as discrete as the step function, is the ramp function. And the ramp function has a particular moment in time which it starts, start time. It has a particular slope, and it uses yet another argument, which is the end time. And if you use this equation, you can actually have a particular ramp up from an initial value at a particular moment in time to with a particular slope to a particular end time. So this is basically a means of, for instance, implementing policies in a slightly more gradual way at a particular moment in time. So that's the second type of function, the second function that is very useful. The third function that is very useful is actually a built-in function, and that's time. Time is pre-specified in these models because these models are all about simulating things over time. So the way in which you can use time is by calling it as a shadow variable that is with the button that with these weird bracket brackets. And using that button, you can actually add any previously pre-specified, every variable that has already been specified in your model, and time and several other variables are pre-specified by the program, so we can call it and we can include it. This is very useful to do something that we can do way better, but which I'm going to deal with in the more advanced lectures. That is to add data series or time series to a model. And say, for instance, we want to add a oscillatory pattern to a model. So not an oscillatory pattern that is generated endogenously by the model itself, but for instance, just to test whether seasonality has an influence on our model. Then we can add, for instance, use a sine function, sinus, of time. And if you do this, then you actually get an oscillatory pattern, right? The problem is that this oscillatory pattern is most likely not the one you want, because it's between 1 and -1. And well, from here, you can actually tweak this. You can, for instance, shift it up. You can, by just adding values, you can compress it by dividing the sinus by some value. You can, for instance, increase the frequency of the oscillations, or decrease the frequency, or just shift the whole function left or right by just using what you probably learned in Tinium before in high school or at the university. So for instance, if I want to just have a seasonal function with a peak in summer and a peak in winter, then I can write that right away as 0.5 plus 0.5 times the sinus of time plus pi, so that's 3.14 divided by 2. And this is going to give you a function that is shifted up and then compressed, so that it's between 0 and 1, and that I'm going to have a peak round about the start of the year, or probably around month 12, and also with a peak somewhere in the middle of the season, so around month 6 or 7. Okay, now the next function, or the next two functions that are very useful, are the following. A max function and a min function. So the max function takes the largest of two values or functions, while the minimum takes the minimum of two values or functions. So that also means that the max function can be used as a floor. Say, for instance, we have our oscillatory pattern, and we want to only have the positive peaks and nothing below 0. Then using a max of the particular function that we have here, or the value 0, which is the other function there, actually allows us to select just the positive part. Because if it is positive, then the maximum of the function, or 0, is the function. But when it actually turns negative, then the maximum of the function, or 0, is going to be equal to 0. So in that case, you actually just get the positive part of your function. So with a max function, you can set a floor. With a min function, you can actually set a ceiling. For instance, if I'm using if I'm taking the minimum of this function, or 75, then I'm going to take the minimum here. Well, wait. I'm going to take the minimum here, the minimum of these values, and here we have the value 0.75. Then it's going to take the minimum, 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 and oh, here 0.75 becomes the minimum. So it's taking the minimum, 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 and so on. It will go on taking the minimum, 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 and then here again 75 is the minimum. Okay. Now, if I combine both, then it becomes interesting. If I combine both and I take a maximum of this function, or 0, so I'm setting a floor, and I extend this with a minimum of this maximum of this function, but then of a value 0.75, then what I will obtain is a function that is going to be limited at 75. Then it decreases again. It will never become negative. And then here we go again. So here we have 0.75, and here we have a bottom at 0. Now, if you compare what we did here and there, then you will see that they are proxies for instance, doing the same thing. Getting a seasonal effect where, for instance, most crimes are happening either during the dark days in the middle of the winter, or in summertime when people leave their doors open. So yeah, the min and the max function are used to set floors and ceilings, but also to select the smaller of two functions. So next, we get to delays. And in these simulation models, we often use material delays and information delays. Those are the two big categories of delays. So, but within these big categories, we use delays of very different orders. For instance, the first order, second order, third order, and also delays with an infinite order. I'm going to start with the first order delays, both material and information delays, and then I will extend it to higher order delays. This is a pretty technical explanation, but delays are really important in terms of the influence they have on model behavior. So therefore, it's pretty important to understand what is really going on. When you're modeling, you're just going to use the functions that are already in your program, but it's good to know what underlying structures there are, or what the underlying structures are of delays. So a first order material delay. Let's start with that one. First order material delay. We can actually model this with just a stock, an inflow, an outflow, which is proportional to the stock. Proportional also, well, and the equation in the outflow is basically the stock divided by some delay time. So that basically means that whatever goes into the stock in the material delay stays there for a while, is homogeneously mixed, and is actually leaving the stock as the value of the stock divided by the delay time. So this is equal to stock divided by delay time. Let me sketch what that actually means in terms of the behavior. Suppose we have an input that is just a step function that we've already seen. Then the question is, how is this transformed by the first order material delay, and how does it come out? So what is the response of the system to this input? Think about it. What is actually happening here is that starting with a value at 0, nothing is entering, nothing is entering, nothing is entering. And all of a sudden, we jump to, for instance, a value 10. So that basically means that from moment, let's say, 5 on, we will add 10 to the stock. So before the time, values were 0, right, until 5. Now at 5, there was nothing in the stock. Stuff will actually get into the stock. So from moment 6 on, there will be something that will be flowing out of the stock. What? Well, the stock value divided by the delay time. So say, for instance, the delay time is 2. Then what will flow out of this system is 10, which was entered in step 5, divided by 2. So here we will have the value 5 flowing out of our system. In the 6th step, we do not only have an outflow, but also, again, an inflow of 10. So that basically means that we still had 5 left in the stock, plus 10, that's 15, divided by 2. So in the next time step, we have 15 divided by 2, which is 7.5. 7.5 flowing out of our system. In the next time step, we still had 7.5 here. 7.5 plus 10, which is 17.5. So divided by 2, in the next time step, we have 8.75 that is leaving our stock. And so on and so on. So that basically means what is happening here is convergence from towards 10, from 0 towards 10. So bringing these two together, the response of our system to whatever is happening here with the first order material delay is convergence towards 10. So if you have this step as an input to a first order delay, then the response of the system is actually convergence towards the step value. That also means that there is some sort of delay, and this is not what you are used to when you're talking about delays. What you are used to is that stuff is just going to be delayed with, or that the response is delayed with an exact amount, a particular amount, and that it is showing the exact input, but then delayed. That's not the case with the first order material delay. Now, a second order material delay is just another one of these delay structures. So let me add one. And whatever flows out of my first order delay is then added to my second first order delay. And in this case, we're going to be interested in whatever comes out of our system here versus whatever went into our system here. By the way, for first order delay, I forgot to mention that we are, of course, interested in the input and how that is being delayed by the structure. So we're interested in the output here. Now, if you look at this, then this cannot be the second order delay because it's going to be delayed with, for instance, 2 weeks here and then with 2 weeks there. So the average delay now is 4 weeks, while we just want a second order delay, but still with the same delay time, which is 2 weeks. So the second order delay is actually one where the delay time, which is here, sorry. So where the delay time is divided by the order of the delay. Yeah. So dt divided by the order. So in this case, 2. So stuff will go in, it will come out, but then it immediately goes into the second stock flow structure and it comes out. But everything is a little faster. So we will, for instance, with a step input here, have the green response there, which is the input here. And then the question is, how is that going to be delayed then there, and how does it come out? Well, the answer is that it's going to be delayed a little more. So everything starts a little slower because we don't have an output in the first step after we had an input to the system. Everything is going to be a bit delayed, and then things go just faster and you converge to the top. Now this is already pretty fast for a second order delay, but this is basically the principle that I want to show, that with higher order delays, you actually get always a slightly more delayed response, and then things speed up and you get convergence to the step function, but then that convergence is actually much faster. So a first order response is an immediate response, and then it converges towards the step function. A second order delay starts a little slower and then converges. The third order response is even slower, so this is really going to be an S-shaped curve, but then faster in terms of its convergence, and so on and so on. So if you push this to the limit, then at an infinite order, you actually get exactly the delay, for instance, the 2 weeks delay, and then an immediate, well, in this case, an immediate step up, because we are sketching the response to a step function. This actually means that the infinite order delay follows exactly the behavior of the input, but then delayed by the delay time. That's probably what most of you expect if you talk about the delay. But in many cases, delays are somewhere in between, let's say third order delay, where there's not an immediate startup, but then everything accelerates, and then you finally get convergence. Let's look, for instance, at what this means in terms of, for instance, a batch entering a second order delay, or yeah, some sort of a pulse or a peak that enters. So let's say this peak enters into our system and is delayed by 2 weeks. 2 weeks. Well, if this is an infinite order delay, then this means that this is going to be replicated and you get exactly the same response out after exactly 2 weeks. A first order response would be as follows. If this goes in, then if we have a 2-week delay period, then half of it will actually be leaving the first week, and then the second week, half what is left will leave, and so on and so on. So basically what you will get is some behavior, output behavior like this. A second order response will then be slightly slower, and so on and so on and so on. But that shows a very different type of behavior then, because it will start out without immediately emptying half of it, but it will actually start out at 0, and then it will increase and decrease and so on. Well, this is not very well drawn, but you get the point. Now, what I want you to do is to test these different delays and what they do to different inputs in the model, because it's very important to know and understand the way in which delays change the behavior in a system. Very often, we want to get rid of delays in systems or to add delays in order to get more desirable behaviors. So that's what I wanted to tell you about the orders of delays. But let me go back to the big differences between material delays and information delays. So in a material delay, everything that goes in also needs to come out. And in information delays, that's not the case. Now, the underlying structure of an information delay is an inflow to a stock, and then there's something going in, and we are interested in the stock value as whatever goes out. So we're interested in the stock value, while in a first order material delay, we were interested in the outflow. The equation in our inflow is actually the value of in minus the stock value divided by the delay time. So here we also need to add the delay time, which we also had there. Interestingly, if the delay time remains constant over simulation time, then the behavior of this first order information delay is going to be exactly the same as the first order material delay. And the same is true for the second order information delay, the second order material delay. So the only real big difference happens when the delay time is actually variable. In that case, the material delays conserve material, people, whatever goes into these stocks needs to come out. So say, for instance, if delay time is significantly reduced, then that means that all of a sudden more needs to flow out of our stock flow structure. While in information delays, that's not so much, that's not really true. On the other hand, or not on the other hand, but another difference between the material delay and the information delay is that material delays are really used to account for positive things flowing in, for instance, people, or and so you cannot have negative people flowing in. While in information delays, that's really not a problem, because what is really happening here is that if the inflow is bigger than the stock value, then the stock value will increase with a particular value over time, namely in minus the stock, and that whole divided by the delay time. But this is very often also negative in the sense that if whatever is kept track of is smaller than the stock value, then we actually have a negative number here, and divided by delay time, which is also always positive. This is going to be negative. So we will have a negative inflow, which basically means that the stop value is decreasing. Information delays are really used a lot to smooth. So you could think of this as some averaging of particular values. So say, for instance, you have stop values that are very, very jumpy, then a smoothing structure can be used to smooth these values and to get a more smoothed out pattern. And the second order information delay in structure-wise is actually the same as with the second order material delay. You would basically add another stock flow structure. So there's an inflow here. And whatever flows out here goes in here. And again, we have dt, stop value, and the equation here is the same as there. And again, it's a second order, so therefore we divide dt by the order of the delay. So this is basically the technical explanation about delays. But what I really want you to do is to test all sorts of, or the response to all sorts of inputs in different types of delays. And quite often, making more advanced versions of delays means that you would, for instance, have to combine delay fixed, so an infinite order delay, to keep something as it is, and then use another variable, for instance, to then let whatever is kept in memory for a particular period of time, let it flow out of your system with some, for instance, third order delay. Let me give you an example of that. So until very recently, students at TU Delft studied for an average of 7.5 years, although the study here is just a 5-year program, 3 years bachelor's, and then 2-year master's. But students would actually enter, and then they would stay in the system for at least 5 years. And after these 5 years, some would graduate, but not most. Most would actually graduate after some time, and some people would just keep on studying forever. And the average of this would be 7.5 years. Now, in order to model this, you would actually have to keep your students in the system for 5 years, because they cannot graduate within 5 years. It's only 5 years plus weeks or months. And then from here on, this could actually be approximated with the third order delay. The third order delay with then 2.5 years delay in here. And then you would actually be able to replicate more or less what is happening or what was happening in the real system. Nowadays, this has improved a lot. So that's what I wanted to tell you quickly about delays. They are very important. And this is really the start of these different functions. Then all the other stuff is best explained immediately on the computer. So there will be a next video that starts. I'll make that tomorrow morning. And in that video, I will actually do everything on the computer, everything I've done so far, plus all the additional exercises that are, not all the additional exercises, but I will give you the explanation, the fast feed-forward explanation of all the stuff that is in the learning path of the second week of the systems modeling course. See you then.